Hello. Today we are going to see a very interesting problem description, and this has got to do with more of geotechnical engineering, bridge engineering, and this particular problem is related to computational fluid dynamics. So we are going to consider a particular bridge which is about 500 meters span, and it's constructed across a river, and the river flows with about say 15 meter per second, and we are going to understand the fluid dynamic parameters, the characteristics. So when there is a bridge constructed across a river and perpendicular to the span of the bridge is the flow of water, and it flows at the rate of 15 meter per second, and we are going to find out what are the forces that is going to act on the members. So we'll be trying to understand the flow dynamics right from the foundation, that is from the pile cap, and the pier cap, and then over the girdle. So here we have a schematic, uh, a representation of the bridge, and there are about say 4 or 5 bays, and each bay spans up to 50 meters, and in between two bays we have two structures. So we can call them as pier walls and the pile, and this is under the assumption that the total height of the bridge is about 25 meters, and that is from the strata. So which means like there is a terrain beneath the river, and these are piles that are constructed on the foundation. So it's a 3D solid model of the system. So we have a trapezoidal member, and over that we have a group of piles, I mean the columns, and on the column is what we have the structure, I mean the superstructure. So this is the superstructure, and this is the deck, and you have the columns here, circular columns, and all the circular columns are constructed onto the pier cap, and then you have the pier wall, and that is on the riverbed. So we have spans. This is the first span, the second span, the third span, the fourth span. So 4 different spans, and then 1, 2, 3, 4, 5, 6, 7, 8. 8 different structures. And now beneath the bridge is where the water flows. Okay, so now we know that when there is an obstacle placed in front of a regular flow, the flow can be laminar or turbulent. Okay, and we assume that the flow is perfectly streamlined, and then we are placing an obstacle in front of the flow. So what happens is the flow diverges. Okay, the flow diverges based on the circumference of the structure, that is obstacle in it. Okay, so now here in this case it's a circular structure, the pile. Okay, and we can see up to the pile, I mean the pier wall, and then you have the pier cap, and on the pier cap is the columns, and then the columns are connected to the superstructure. Okay, so since it's a circular structure here, a circular section, the flow is going to be circular. So there is going to be a divergence in the flow, and from that, the flow is again going to, build up pressure. So the velocity of the flow increases from that point. So we assume that the flow is from this direction, that is like this, and it goes this way. And these are the members that is going to obstruct. Okay. And when the flow is obstructed, there is going to be a divergence, and that can even cause vortexes. It can cause vortexes. Okay, and there can be a lot of pressure differences. There can be, because of those pressure differences, there can be even suction. Okay, you would have seen whirlpool. There can be vortexes. These vortexes are nothing but eddies. These eddies are nothing but it's a circular motion system which is in circular motion that can pull anything which comes out. Okay, so now here we have modeled the structure, and we are assuming that 80% of the structure. So let's say 70% of the structure is about reinforced with the steel, and about 30% of the structure with concrete. Okay, so now what we do is we are defining a computational domain. So when I explained that this is a flow dynamic related problem, okay, we are going to be more interested with the hydrodynamics, the flow dynamics. Okay, so when we are interested about the hydrodynamics, we need to define what is air and what is water. So which part of the domain is going to be established with air, and which part of the domain is going to be established with water. So what we are doing is we assume that the water is up to this location. Okay, and the brim of this particular pier cap. So let's assume that the water is flowing, okay, up to the brim of the pier cap. That's the assumption that we are going to make. And the velocity of the flow is across the y-axis. So here we find the global coordinate, and the global coordinate says the length of the bridge is nothing but the x-axis, and the perpendicular to that is the y-axis, and the velocity of flow is going to be across the y-axis. Okay, so now this is the global coordinate system, and from the global coordinate system we can create as many local coordinates as possible. So when we assume this structure, we can have a local coordinate system, and when we are considering this part of the structure, there can be a local coordinate system. So likewise, we can create as many local coordinates as possible. Okay, so now we have assumed certain things. The materials that we have considered for the simulation is concrete as well as steel. Now, since this is a computational domain, okay, we are not worried about the material density or the properties. We are just worried about the shape. So anything related to computational fluid dynamics, we will be looking only for the shape of the structure. Okay, and we also look for the dimensions. Okay, that's pretty important. So the total height of the structure is about 25 meters. The single span is nothing but the distances between the center distances between the two pier caps, or maybe the two pile, is the span length, and this single span length is about 50 meters. Okay, and the overall size of the bridge is about 500 meters. Okay, now let's define the computational domain. So this is going to be my computational domain. Okay, and this computational domain says that my bridge is within this particular computational domain, and I'm defining that from the bottom of the pile or the pier, the bottom of the pier. Okay, from the bottom of the pier to the top of the pier cap. From the bottom of the pier to the top of the pier cap is going to be filled with water. So that is the zone with water. And from the top of the pier cap to the top of the deck, the bridge deck, is going to be with air. Okay, so there are two fluids which is going to act. One is going to be the air flow and the other one is going to be the water flow. Now, why we consider both air and water? It's called as immiscible, liquids. Immiscible liquids. So, which means there is going to be certainly an impact of air which is made on the water. Okay, and then it is not going to mix anyway. Like, we are not worried about the chemical kinetics here, or we are not worried about the chemistry part of it. So we are going to just worry about the dynamics. Okay, there are certain amount of air molecules and there are certain number of water molecules, and the impact made by the air molecule on the water molecule. So whatever air is there, it is going to create a frictional force between the air surface and the water surface. Okay, which will happen exactly at the place where the pier cap is mounted. Okay, so now why I am calling it as pier is above the pier I have got columns. Okay, and there is a specific reason that the structure is built like this. Okay, and this particular river at some part of the year there is a probability or there is a chance for the river to overflow. So when it overflows, it shouldn't be dangerous. It shouldn't collapse the structure. Okay, so that is the reason the structure itself is elevated with the columns, and these columns are constructed onto the pier cap. Okay, so the computational domain is this, and within this computational domain is what we are going to understand the or study the hydrodynamics. Now, when we take the actual bridge and when we take the actual river, okay, it is supposed to be considered as an infinitesimal boundary because we need to limit our mathematical computations. We need to limit somewhere. So that is the reason I am taking a specific distance, a specific zone, and within that particular zone, I am trying to make a computation. So this particular computation boundary or the cuboid structure that we find, it is going to be completely filled with what we call as cells, and these cells we call as finite elements. Okay, so in finite element method terminology, as I had explained in the previous episodes where we discussed the statics, we discussed the dynamics of the structures, and we also found out the natural frequency or the normal modes. Okay, so in such places, we break the structure into well-defined geometries, either triangles or its extensions, or square or its extensions, or rectangle or its extensions. Okay, and we also said that these geometrical structures have interpolated points, and these points are what we call as nodes, and these nodes have got a specific purpose and a meaning, and these nodes are points represented on the space which is capable of transferring physical properties. The physical properties like strain, stress, thermal factors, pressure, forces, etc. Okay, point is nothing but it's a simple coordinate. Okay, on the space with x comma y comma z. okay, at the origin at 0 comma 0 comma 0. Okay, so it is nothing but a simple geometrical representation. A dot on the space is a point, whereas a node is nothing but a point on a space that can transfer physical quantities or physical properties from one point to the other. Okay, and it has got a direction vector also. So here, instead of finite elements, we are going to split it into cells. We call it as boundary element, and these boundary elements are finite volumes. We can split it into cubes or cuboids. Okay, and these cubes or cuboids can be called as cells, and these cells can be covered. So in this case we are going to be having immiscible fluids. Air is a fluid and water is a fluid, so there will be certain space or cells that is going to contain air, and there are going to be some cells that is going to contain water. And now we have already defined, I mean, that there is going to be some fluid, so that is going to be, and now here we need to define which is going to be the fluid boundary and which is going to be the air boundary. And as I mentioned, this particular region, that is from the base of the pier to the top of the pier cap, okay, this particular distance is going to be filled with water. Okay, and even the zone which is below that, okay, so from the point from that particular point, okay, below that particular pier to the black line, which is the computational domain, that entire region is going to be filled with water, and anything above this is going to be filled with air. Okay, now once I have defined that, I am going to I'm going to define the fluid cells and the air cells. So here I have got the structure. I mean, this is going to be my computational domain, and this computational domain I am going to split it into cells, and these are the cells that you see, and these cells are going to have the fluids and the air in that. Okay, this can be further refined. Okay, there are certain parameters, and making use of those parameters we can reduce the size. Now, like for this particular model, this is okay, this is sufficient. My flow parameters can be found out with this. Okay, and let me see like what are the inputs that I'm going to consider. So this is going to be certainly a time dependent phenomenon, because the water is going to flow. Okay, at time t is equal to 0, it is at rest, the water particle, and at time t is equal to 10 seconds, that is going to reach some point. Okay, so now let us imagine that the water is going to start from this point. Let us say from this point here, the water is going to start from the one particular end of the computational domain. Okay, and at time t is equal to 2 seconds, it is going to reach the brim of the structure. So at this particular point, okay, exactly at the top of the pier cap, and at time t is equal to 10 seconds, it might be reaching somewhere at the other part. Okay, the flow is going to happen, and the particular water particle at time t is equal to 0, which was at some location, that is transferred, or it has moved from that point to the other point. Okay, so now this is going to be x comma y comma z at time. Time is a function. Okay, so now it's a time dependent system, and now I'm going to define the gravity used, because the entire structure, the superstructure, okay, is going to have a dead weight, and this particular dead load is going to be acting towards the gravity. Okay, so the gravity parameter is also defined along the z-axis, the z axis. So I give it as minus 9.81 meter per second square. That is going to be my gravity, which is going to be towards the z-axis. And now I am going to define a free surface, because there should be a partition between water and air. I told you the air which is moving at a certain velocity is going to impart that particular force onto the water. And how does it impart a velocity onto the water? The air which is flowing, it is going to create a shear onto the water surface. Okay, and this water, the top layer of the water is going to shear with the second layer of the water, then with the third layer of the water. So likewise, this entire tuft of water or the blanket of water is getting carried to the next part. So from at time t is equal to 0, from point P1 to P2, the blanket of water moves, or that particular layer of water moves. Okay, and this is a time dependent phenomenon. Okay, so now this is how the air is going to impart velocity onto the water. Okay, so there is going to be an impact of air also onto the water. Even otherwise, the water is going to be coming from an upstream and it is going to go downstreams. Okay, from upstream it can be flowing from many sources. It can be from a waterfall, it can be from the mountains, or it can be from a river on the upper side of the region. Okay, so the water can come, or I mean it can flow through many means. Okay, and now because of that there is going to be a velocity imparted onto the water. Okay, so that is the flow that we are going to consider, and a boundary layer that is going to separate the water from the air is called the free surface. Okay, so now we have defined a free surface, and now we define what are the fluids. So we are going to take air and water as the two invincible fluids. And now we define the flow can be laminar and turbulent, because I am not going to restrict by saying that it's going to be a laminar flow, or I am not going to restrict that this is going to be a turbulent flow. It is going to be a mix of laminar and turbulent. Any flow, okay, of river, even if it is a sea or even if it is an ocean, I mean the rivers, okay, it is going to be a mixed laminar and turbulent. So now let's consider it as a laminar and a turbulent system. And now let me define what are the initial conditions and what are the ambient parameters. Now this is going to, the entire system is going to be on the environmental pressure, the atmospheric pressure, which is going to be 1 atmosphere and which is nothing but 101,325.44 pascals. And then let me also define that the temperature. Okay, so it's assumed that it's flowing from the river, from the mountain, and it is going to come down as a waterfall, and then it catches the downstream as a river. Okay, and in the due course the temperature, okay, has reduced, has increased from let us say 2 degrees or 3 degrees or say 5 degrees. So from 5 degree, okay, there has going to, there is a potential energy change, and because of that heat and mass transfer, there is going to be a temperature change. So now it has become 15 degrees. So we are assuming that the temperature is about 15 degrees Celsius. And now we have to define the concentration of air and concentration of water, and that is going to be a time dependent function. So we define a dependency, and in what way we are going to define the dependency is, we are going to define here the minimum region, the minimum distance is minus 51.24 meters and the maximum is 74.68 meters. So the 74.64 meters is going to be exactly on the top of the pier cap. Okay, so we are going to assume that 74.68 is the height, okay, exactly on the top of the pier caps. Or we can also increase it in any way we want. If we want to define that the water is going to be exactly flowing across the girder, then I can say, like, I can define the height also to be exactly on the top of the girder. Okay, and now we have also seen, like, the base of the pier, the column. Okay, so that is going to be minus 51. So at minus 51 it is water, and at plus 11.72 it is air. Okay, now maximum is 74.68, which is the top of the girder. And now I am just defining it as 11.72. Okay, so it is slightly above the pier cap. Okay, so now all the systems and everything we have defined. Okay, and now we are going to define that the parameter is going to be varying with respect to altitude. Okay, so now what is why we are taking it as an altitude is this is the base of the pier. Okay, and this is the top of the pier cap. Okay, this is the pier wall, this is the pier cap, and this is the top of the superstructure, that is the bridge deck. And this bridge deck is the height of the bridge deck is 74.6, and the height of the this particular pier wall is exactly resting on the river bed, and that is minus 51. Now let me just hide the computational domain, and let me hide the mesh also, or the finite volume. Okay, now what I'm going to do is I'm going to define my calculations. I need to define like what are the inputs. I have defined what are the inputs. Okay, and now based on the inputs I need to find out like what are my outputs. What are all the parameters that I need. Okay, so now I'm going to find out what is my total pressure, what is my average dynamic pressure. I also need to find out what are the temperatures. I need to find out what is the mass fraction of the fluid. I need to find out what is the volume fraction of the fluid. And I need to understand what is the mass flow rate and the volume flow rate. I need to find out the velocities. I also need to find out is what are the circumferential velocities, the radial velocities, the axial velocities, and what is the total turbulent energy loss, and what are the normal forces, the frictional forces, because these are all the main parameters which is going to affect the entire design of the bridge. Okay, so the bridge is nothing but it's a structure, a complex structure which is going to be constructed, okay, on a specific terrain. Okay, and the terrain can be rocky, it can be clay, it can be any type of, even it can be limestone, it can be a desert, it can be any kind of terrain. And now the harder the terrain, okay, the safer the structure. The reason because the piles and all those things can be driven directly onto the structure, or the foundation can be taken directly from the structure. These hard structures are rocks. Now, if it is a riverbed, then of course we need to go for a auger boring, or we need to drive piles, and we need to stabilize the soil first, because the soils are going to be very loose. It will be a kind of elastoplastic deformation, or more of viscoplastic structures. Okay, and now there is going to be a lot of elasticity induced. Okay, and that can definitely create a lot of disturbance on the structures. Okay, when there is some seismic activity. Okay, so like we find out all these particular outputs, the average volume fraction, the mass, the fractions, and all those. Okay, once we are done with this, we perform the simulation, and we try to find out like how the flow is going to uh, influence more on the structures. So let me just run the simulation. I have run the particular simulation, and let me solve it. And now I am going to use all my 12 cores. Okay, and yes, so the simulation has just started, and now what I'm going to see. Yes, so let me find out all these parameters. Okay, so now this is going to be yes, so this is going to be my flow. Okay, so the velocity the water is flowing from this stream, that is upstream. This is the downstream, or we can say this is the downstream and this is the upstream. So usually, the source is considered to be the upstream, and the sink is considered to be the downstream. So from the upstream to the downstream, let's see how the system is going to function. So this is the volume fraction of the air. So the volume fraction of the air is going to be defined this. Yeah, this is how the volume fraction of the air is calculated. So you can see the flow from the upstream, how the flow is going through the pier. Yeah, this is the pier, and you are able to find that there is going to be a suction here. I mean, a kind of vortex. Okay, it is going to hit the particular pier wall. Okay, it is going to lift, and it is going to create a swirl, and this is how the flow is going to take place. So we'll be able to see the vortexes formed. These are all the eddies. We'll be able to see the eddies formed here. Okay, so this is the volume fraction of air. And now let's try to find out what is the volume fraction of water. So that's going to be like this. The volume fraction of water is going to be like this. So you will find that the blue zones, okay, that is where the water is going to be at, the velocity of the, the volume of the water is going to be here. This is the blue region, and that's going to be 0. From 0, it is going to increase to 1. Okay, so volume of water, the volume fraction of water here at this zone. Okay, so you'll be able to find out, you'll be able to visualize how it is going to become a wave. Okay, and that's the reason, the hydrodynamic equations, the parameters are calculated, okay, using very complex equations, and until we have a specific system like this, it becomes very difficult for us to break the flow parameters. So now once we have determined what is the volume fraction of air and volume fraction of water, let's try to find out what is the change in pressure, if there is any difference in the pressure. So there is no much difference. Okay, it's going to be here. So this is how the pressure variations are going to take place. Okay, so here it is about 546 Pascal. So the 1 atmosphere is nothing but 101325. Okay, and now this is, yeah, so 101325 is going to fall here, somewhere here. So which means it is exactly 1 atmosphere and slightly lesser than 1 atmosphere, because there will be a lot of changes in pressure. Okay, so that's it. Now let's try to find out the temperature. Okay, now we can find that the temperature variation is between 14.65 and 15.17. So which means there is a very small change, a negligible change in temperature also. So, and all these things are happening in how many seconds? About 10 seconds. Okay, so it is not usually 10 seconds. Okay, the actual fact is when you consider the entire fluid domain, the entire river bed, the entire river, from the upstream to the downstream with the entire bridge. Okay, the computation will be, the flow will be for a period of say 10 minutes or 15 minutes or 20 minutes, like what is going to be the. Okay, and that is going to be a very huge computation. There is going to be more number of core processors that we need to go for. This itself is a GPU, the laptop, and that has got 12 cores. So now if I make use of say 28 cores or say about 64 cores, then probably large computations can be done. Okay, so now the temperature is negligible. The change in temperature delta T is negligible. Now let's find out what is the velocity. We know that the actual velocity is about say 15 to 20 meters per second. Okay, that's the velocity which it's called as the resource velocity, the source velocity. Now this source velocity doesn't have any hindrance when it starts from the point, but from the point on the way there is a bridge, okay, with the length of its cross section, and there are about 8 structures, huge structures obstacling the water flow. And because of these huge structures, okay, we are trying to find out like what are the reaction forces that is going to come on the pier walls. Okay, so now this is the velocity, and let's see how the velocity plots. So we are able to find, because of that particular hindrance, you can see how the flow. Okay, so this is how the flow is going to occur. Okay, hope I mean you are able to visualize it. Okay, now let's try to find out the volume fraction of air. Now, what volume of air is going to participate in the hydrodynamics, the flow? That is what we mean by this. So you will be able to see like this much air. Okay, so 0.18, 0.27, 0.36, 0.8. Say about 70% or 80% of the air is going to create, like an impact, or it's going to influence the flow of water. Now let's see what is the volume fraction of water. It's going to be the other way around of that, I mean the mirror of it. So here we'll be able to see like how see about 20, 25, 27, almost about 30% of the flow. The water, the 30% of the water is going to be disturbed by the air fraction. Okay, that is what we mean by this particular plot. Yeah, so now let's try to find out the axial velocity. So now this is the axial velocity, and this is exactly is what we'll be looking for when we are studying the members, the structures. When we are designing the structures, we are going to define that this particular structure, okay, has to sustain the flow, okay, which is about this much meter per second. Okay, so now what happens is the total size of the bridge, the total number of piers which is going to be on the foundation. Okay, and these piers are going to be imparting a resistance on the flow. So which means that these piers have to be designed for that much impact. The flow, whatever flow impact is going to come on the structure, it is supposed to be taking that load. Okay, so it is nothing but a direct pressure. Pressure is nothing but force upon unit area, and we'll be able to approximately find out like what amount of or what volume of the structure is need to be designed. Okay, so now from that we design the structure. Okay, for direct stress, the bending stress, and the combined stress. Okay, and we also calculate the shear stress. We find out the members, what should be the area of steel, what should be the area of concrete, and based on that we will find out. We'll integrate it across the height, and we'll find out what is going to be the volume. So this much cubic feet of concrete needed, and this much cubic feet of steel needed. Okay, so now this axial velocity with the axial velocity and the circumferential velocity. So now circumferential velocity is nothing but the hoop stress. So as I told you, the pier wall is circular. Okay, and anything circular, there is going to be a force which is coming on a circular member that is going to exert a hoop stress, a reverse hoop stress. Okay, so this is that particular velocity, the circumferential velocity, and we'll be able to find. Yes, we'll be able to find that. Okay, so this is the zone. Okay, and this particular region, this has got a greater influence. So there is going to be, yes. This is how the circumferential velocities are calculated. And now we also find out what is the radial velocity. Okay, so now this is the radial velocity. Okay, now since my computational, I mean the coordinate system, the global, this is the global coordinate system, the local coordinate system is at this point. Okay, and now once the local coordinate system changes its position, automatically the center of gravity of the structure also changes. Okay, and now when the center of gravity of the structure changes, what happens is all these accumulations of blue color, okay, these contours, whatever accumulation of these contours we see here, that is going to get dispersed. Okay, that's going to get dispersed. So now let's try to find out the root mean square velocity. Okay, and now this root mean square velocity is going to be the component of your circumferential, your radial, your axial, and the average velocity. So this is going to be the relative velocity, root relative velocity. Okay, so now we have found out like what exactly the flow and how the flow happens, and this is a very complex phenomenon. Now it can also change. We can also create a bed, and we can also assume that the terrain, the river bed is going to be of this particular strata. It is going to be highly elastic, and on that there is going to be a pier wall raised. Okay, from the pile there is going to be a pier wall raised. So you will have a pile. The pile is going to have a cap, a pile cap, and over the pile cap is what we build a pier, and on the pier we build a pier cap, and the pier cap is the member, okay, that is going to contain or that is going to hold the superstructure, the bridge deck or the girders. So that can be a pre-stressed girder, or it can be a post-stressed girder, it can be box girders. So like many different types of girders are there, depending upon the usage of it. Okay, so now there are. Let's imagine that on the ship deck, the bridge deck, there is going to be a road. Okay, it's a double lane road. There is going to be huge rolling loads, braking loads, traction loads, and now all those loads that is going to come on the superstructure. Okay, these kind of loads are going to be taken by the expansion joints as well as the bottom PDFE bearings or elastomeric bearings. These are all the structures which is designed to take both movements as well as rotations. Okay, so now the structure can take care of those, and now the structures which is beneath this is supposed to transfer all those loads to the riverbed. Okay, and now the impact of those, the vibrations on that ship, I mean the bridge deck, because of the vehicles or the moving loads or influential loads or rolling loads. Okay, that is going to impart some load on the substructure. From the substructure, it goes to the pile, and then from pile to the riverbed. Okay, so now there is going to be a fluid and a structure interaction. The fluid is nothing but water. Okay, and the structure is nothing but the bridge structure. So the next episode will be seeing like what is going to be the vibration or what is going to be the normal forces exerted on this. Okay, so even from this we'll be able to find out the normal forces. So we have defined. Okay, so now this is going to be the yes. So now I am going to find out what are the okay, let's say the axial velocity. Axial velocity at this particular structure. So this is going to be the axial velocity plot. Okay, so now let's find out what is going to be the normal force. Okay, the normal forces, the shear stress parameters, and the turbulent energy, etc. Yes, so we have the normal forces here. Okay, so the frictional force is here. Okay, so which means it's about 100, 3,200 kilonewtons. Okay, so now this is newtons. So you can convert it into kilonewtons. This is going to be 3,249. So about 3,250 kilonewtons is the frictional load between that water and the pier. Okay. Now the normal forces. So the water which is going to hit the pier wall, okay, that is going to impart a force of this. Okay, this is in newtons. So again 2.31 into e raised to say 5. Okay, kilonewtons. The turbulent energy is 0.031 joules per kg. Okay, so now let's try to find out what is the circumferential velocity. So you will find, yeah, this is the circumferential velocity. Okay, so let's reduce the size. Okay. The circumferential velocity is this. Okay, so now let's try to find out uh, the mass flow rate, the volume flow rate. Okay, so there is, yeah, it is 0. And now let's try to find out what is the volume fraction. Yeah, this is the volume fraction. Okay, so it increases, then it stagnates, and then it slowly comes down. And here it is 0.5, that's the maximum, the volume fraction of air. And here it is the volume fraction. This is the volume fraction, and this is the number of iterations. So the stability has come exactly at 70, yeah, 70th iteration. So 70th iteration is about 0.5. Okay, now let's try to find out what is the average circumferential velocity. Yeah, average circumferential velocity we have already found out. Instead of that, we'll find out what is the how does the turbulent energy vary? Yeah, this is how the turbulent energy is going to vary. This is the average velocity, this is the turbulent energy. Okay. Now let's see the mass fraction of air and the mass fraction of water. So the mass fraction here, it is here. Okay, and now that so this is the mass fraction there. Yes. So it increases, then reduces, then again it goes, then dips down, then again it goes. So these are all the zones, with respect to time, there is a change. So the altitude is going to change. The flow is going to change with respect to that particular altitude. That is what we see here. Okay, so let's try to revise what exactly we saw. Today we studied the hydrodynamic aspects of a river, okay, and where a bridge is constructed across the river, and the river flows at a speed of 15 to 20 meter per second, and there is the influence of air above, and the air is also moving at a certain velocity that's going to create an impact on the flow of water, and we are interested in finding out the flow parameters of the water, the flow, the river, and at the same time we are also interested in finding out the mechanical features, I mean the parameters of the bridge. Okay, what is the mechanical aspects of the flow on the structure? Okay, so that also we found out. We found out the normal forces, the frictional forces. Okay, and we determined what are the axial, radial, circumferential velocities. Okay, and we from those parameters we arrived at the normal forces as well as the frictional parameters and the shear parameters. Okay, so with this, let's complete this particular episode here. And as usual, let me just try to once again remind you for subscribing and sharing it to all your friends or budding up engineers who will really find it very, very important, for their career. Okay, and this is going to be a more of, I mean, this is a more of a practical approach, and all my episodes are some or the other way related to the actual practical, I mean, the actual problem, the real time problem, and a solution for that particular problem. Okay, and now this has got a lot of explanations, and I certainly recommend you to go through the theoretical aspects of the practicals what we have seen here today, and I would also recommend you to try to understand the fluid dynamic parameters, try to understand the core of fluid dynamics, the flow equations, the flow parameters, the mechanical aspects. Okay, and now how the fluid part and the structural part can be integrated. What is a fluid structure integration or a fluid structure interface? Okay, now these are all highly nonlinear problems. Fluid structure interaction exercise are all highly nonlinear problems. Okay, and it becomes very difficult, okay, when we don't have a proper tool. Okay, now here we have a specific tool in application in computational fluid dynamic system, and with which it was easy for, I mean, we were able to find out the structural parameters also. So kindly subscribe, share, and pass on your valuable comments, and let's make it a more interactive. Okay, and only with your valuable comments we'll be able to make it more interactive. Okay, so thank you very much for your valuable time. Okay, and the time that you have spent for knowing more about the these kind of interesting problems. Okay, thank you.